The presence of intelligent systems over the past few decades have grown exponentially. However, despite these systems having a high level of capability to achieve its task goals, there is a high level of collaborative human interaction required to have these machines actually serve its purpose. For example, ChatGPT requires the questions to be presented in a certain way for it to provide the relevant information. Additionally, autonomous vehicles serve to reduce human error through sensory-based methods to track the lane monitoring and also to have warning systems in case of blind spots and obstacles. Collaborative robotic systems, on the other hand, serve to reduce physical human workload in the manufacturing domain and to also serve as therapeutic agents in the healthcare sector to treat various neurological and psychological disorders. On a separate note, human mental workload can be assessed through electroencephalography based methods to track the neural activity during individual performance of different tasks. Some of the prior work have assessed how this human mental workload varies in the cockpit amongst aircraft pilots and found that high levels of autopilot in turn actually led to inefficient decision making and passive monitoring. Therefore, there is a need to assess this neurocognitive states of the individual or the human during these collaborative scenarios with AI-based robotic systems. Therefore, the main aim of my dissertation is to assess the variation in human mental workload and to establish a neural interface wherein the robot has access to this neural mental workload and in turn modify its level of involvement to ensure that optimal brain states is maintained and also like high levels of task performance is maintained. Some of the previous work which I've carried out found that during these collaborative scenarios, the amount of mental resources allocated towards the task was much reduced in comparison to when participants performed by themselves. However, there was an inefficient allocation of the neural resources towards the attentional processes, which was towards the robotic teammate. Another effort on the same vein found that high levels of robot involvement actually led to reduced cognitive workload and high levels of performance when the task difficulty was really high. Therefore, future work will look to establish a brain-computer interface-based system which can have the robotic system adapt to the changing brain dynamics of the individual such that it increases its level of involvement when high levels of mental workload are observed and it reduces its level of involvement when the mental workload levels are regained. Overall, this work has the potential to inform the development of adaptive systems using biological signals instead of bio-inspired methods which use various computational frameworks.